So I hope you can all see my presentation now. The title is Against All Odds on the Robustness of Probability Sample Against Decreases in Response Rates by Piotr Jabkowski, Marta Kołczyńska, and myself. And I would like to thank to all of you to come here hearing our presentation. And I hope we get much critique so that we can make the paper even better than it is right now. So here's the structure of my presentation. I would first like to motivate the research question a little bit. Then I would provide some theoretical background, and this theoretical background will inform our design concerning case selection, identification of causal effects, operationalization of the key concepts, and estimation strategy. And then I will present the most important results of all that. And finally, the conclusion concludes. So let me start with the motivation. As we all know, response rates of survey decline all over the place. I have listed here quite substantial numbers of papers who report on this decrease of response rates over time. The numbers that you see here refer to papers which you can find in the handout that Marta put into the chat. So if you want to have details on this literature, look that up. What I want to show here is that there is really lots of literature showing that, and I think nobody really doubts that this is the case. Of course, loss of response rate leads immediately either to a loss of precision because we have a smaller numbers of observations, or an increased costs if we try to counteract against this loss of precision by a longer fieldwork time or whatever mechanisms we use to increase the response rate against this evolution. And perhaps, but that's actually not automatically the case, the decrease in response rate may also lead in an increased unit non-response bias. There have been papers around that looked at that, and the older papers usually say that there is no such connection, but there's also a newer meta-analysis who said that there is some association between the response rates and the non-response bias. These low response rates actually led pollsters to more and more opt out from probability sampling. In a way, they say that probability sampling no longer leads to probability samples. So we could start with non-probability sampling from scratch and use weights and modern statistical techniques to counteract problems of non-response bias. So in that sense, some pollsters at least, but also social scientists sometimes said that probability sampling has actually become obsolete. We no longer need to use it. We have other techniques to come to valid descriptions of the society, and perhaps also to valid causal inferential statistics. This question on whether probability sampling or non-probability sampling is highly debated among survey methodologists, but also outside survey methodologists. There's even in Germany, there is a legal issue on this going on, because some of the pollsters try to forbid another pollster to use the term representative for their non-probability sampling techniques. So against this background, our research question is there evidence for the feared decrease in sample quality due to non-response? So that's a very simple question, and we will look on that systematically. Others have done this before, of course, but we think we deviate from previous studies in several aspects. First of all, we are using so-called internal criterion of representativity, which has been proposed a long time ago by Wolfgang Soder, and which also I made public in an older paper from 2007. Instead of the more frequently used R indicators or external benchmarks. That is the technique that is more frequently used. Each have their pros and cons. We don't want to go into the details of this discussion, but just look into the paper for this. One advantage of the internal criterion is, of course, that it is much easier to calculate or to estimate, and that gives us a much larger data set than all the previous studies. Namely, we use 739 different surveys. We have a more European perspective, while most of the other papers look predominantly on American surveys. We use, and that's perhaps the most problematic part, we use a dedicated causal approach using directed acyclic graphs to more or less formally derive the adjustment sets that are necessary to answer our question, and that's will a large part of our presentation will on how we use this directed acyclic graph to inform the research design of our paper. And finally, we use a broad statistical approach that combines non-parametric with several kinds of parametric techniques as well. So, theory. The unit non-response bias is clearly defined by Jelke Bethlehem in an older paper. There are various ways to write down the definition of the unit non-response bias, but I use here this one. So the unit non-response bias in a simple random sample for the sample mean is the covariance of y and the response probability divided by the mean of the response probability. So these two features, the covariance, the relationship of some variable of interest with the probability to participate in a survey, this covariance, and the amount of the bias itself, they both together create the unit non-response bias in a nonlinear, using a nonlinear function. Thereby, the unit non-response has kind of a direct effect on the unit non-response. The non-response has kind of a direct effect on the unit non-response bias, because for a given covariance, the unit non-response bias gets larger the lower the response rates get. Therefore, in this directed acyclic graph, we take this definition to the following causal statements. So non-response affects bias directly, while the variable of interest affects bias by its correlation with non-response. So that's our way to show this formula here in graphical terms. Then, of course, non-response has its causes itself. One is perhaps the survey climates, so these kind of survey fatigue and all this stuff might affect non-response, we say. And then also the survey mode and the sampling design might affect non-response. And we put those two survey mode and sampling designs together into the concept of a survey characteristic. Both the survey climates and the survey characteristics, of course, also have their causes. So one cause might be time. So with time, over time, the survey climate might have decreased for whatever reasons. We don't care about these whatever reasons. And that might then decrease or increase non-response in turn. And over time, perhaps also pollsters have changed the way they design a survey, and that then might also have affected non-response. And there are, of course, also country-specific traditions in the survey characteristic. For example, what kind of sampling design you use is definitely dependent on the sampling frames that are available in a country, and it is also a function of the money that is available in a country, since a simple random sampling, for example, is quite expensive, while random root sampling is much less expensive. And of course, also this country culture is also something that defines that affects the survey climate. And then another thing, this is barely visible. Of course, when we look at the non-response bias, we, by definition, need to look at the non-response bias of a certain variable that we have to measure. So instead of the bias of variable y, in variable y, the non-response bias in variable y, we look on the non-response bias in the measured variable y. And therefore, of course, there is the possibility of non-sampling errors that affects this measurement. And these non-sampling errors might, again, be a function of survey characteristics, country, and time. So that's our view of the data generating process that leads to unit non-response bias in the world. So this is here expressed in terms of the population, not of a specific sample. Is this model of how the world works correct? No, of course not. It's a model. It's a simplifying model. There is no model that is true. It's a simplifying model. We hope that we have all things in the model that are necessary to come up with an unbiased estimates of the parameter of interest that we are interested in. That's what we hope, and that's what you might want to criticize when we come to the discussion. So what are our research questions then? Well, we would like to estimate the total effects, the total causal effect in terms of the counterfactual concept of causality, of time on non-response, of time on non-response bias, and of non-response on bias. That's what we are striving to estimate. So far for the theory. Now on the design. I would like to start with the case selection to give you an idea what data we have, and then we will put this case selection into this directed acyclic graph to come up for a specific research design that we are using. We are using the data set sample practices in Europe, which we abbreviate with the term SAFPE, which has been collected and maintained by my co-authors Jabkowski and Kołczyńska. So this is really a very, very fascinating data set, which had a lot of users, and I'm very sure that there will come up lots of papers out of this data set. Because this data set has information on European surveys spanning over the time from 1981 to 2017 from 4 major European surveys.
Já, halló, Sessili hérna, Hagstofu Íslands.
Hello?
Excuse me.
Was this a question, or what was this? Was this an accident?
I think it was a mistake. Somebody made a mistake.
Okay.
Microphone, please keep your microphones in silent, please. Sorry, Ulrich.
No problem. So I go on. So this has 4 major European survey programs, namely the European Quality of Life Survey, the European Social Survey, the European Value Study, and the International Social Survey Program. If I know correctly, the European part of it, and not the worldwide part of it. Overall, these are 1,145 surveys, so there's much of work going into this data set. From this data set, we selected a subset, not a small subset. We selected a subset. We only use surveys carried out in or after 1999. We excluded non-probability samples because the non-probability samples are usually quota samples, and these quota that they are using are too close to the variable that we use later on in defining the non-response bias. We only use face-to-face surveys. We only use non-missing surveys with a non-missing harmonized response rate. We only use data with a non-missing data on the absolute sample bias as we define it later on. So after all this selection step, we end up with 739 surveys under consideration. Now, this data selection process is, of course, not a random draw of the surveys of the world. So we have to include this data selection process into our data generating process model. And that's what we do on the next slide. Here you just see how many surveys we have and how many countries we have, how many ways we have in the various programs. So you see how the surveys distribute over all this here. And I go on to this DAG integration because that's perhaps the most important part. So what we do here is we add a 0-1 variable selection to our directed acyclic graph. You see this here, selection. So this variable is 1 for those surveys that have been selected into our data set, and it's 0 for those surveys that have not been selected. We believe that the selection is partly a consequence of country. Of course, that is the case because we only use European countries, right? And we only can use those countries which are able to finance the participation in the project. So this is clearly a function of country. It is also a function of the project because we only use those surveys that are part of the project. And then time also matters for the selection because, I mean, clearly we have removed all observations before 1999, but also whether certain surveys can be done varies over time a little bit. So sometimes some country cannot participate in a project because of financial problems and so on. So we use here a square sign for this variable because our whole analysis is conditioned on the selection. We only use those surveys which have been selected by us. That is here expressed with this square bracket. In DAG terms, this selection variable is now a so-called collider variable on various paths between our exposure variables and the outcome variable. So time is an exposure variable, And non-response is one of the outcome variables in one of our research questions. Now look at the following path. We go from time to selection, then to country, then to survey climate, and then to response. On this path, this variable selection is a so-called collider variable. A collider variable is a variable that blocks all associations. So normally no association, statistical association will be transported through these paths. But if you condition an analysis on a collider variable, the path will get opened, and that means there is an association running through that path. So because we condition on selection, there will be a statistical association between time and non-response that is due to a causal process that goes on this path. And this would bias our estimate of the total effect, because this is a non-causal path. We go backward one of these arrows here. That's the idea of this variable here. And if you never heard about all this, then I recommend reading the nice introduction to directed acyclic graphs by Felix Evert here. That's number 33 in the bibliography. So from that, we go to the identification of the causal effects. We go to the identification of these causal effects, and what you see here is in red all the paths, all the arrows that contribute to a biasing effect for the total effect of time on non-response. So when we look on the total effect of time on non-response, and if we just calculate the bivariate association between time and non-response, this will not be an estimate of the causal effect, because there are so many passes that are non-causal, which all appear because of our selection process. So what we want to do is to control for other covariates to get rid of those biasing passes. That's the entire idea of identification using directed acyclic graphs. So what we propose is, for example, we could control for country. If we control for country, lots of these biasing passes disappear, but still there are some biasing passes, for example, from time to selection to survey characteristic to non-response, from time to selection to project to survey characteristic to non-response. So that will perhaps make the problem a bit lower, but still we have biasing passes. We cannot identify the causal effect. We might want to use project as a control variable, but then this would be really a very bad adjustment set, because we only get rid of this biasing pass here, but we have a lot of other biasing passes. And what we also get, we get a so-called over-control bias, because if you look at the blue lines here, we have from time to project to survey characteristic to non-response, we have a path that links time and non-response only in the direction of the arrow. So this is a causal path that is part of the total effect. So we should not control for project, or controlling for project would over-control the would be an over-control, because we get rid of a causal path that should be part of the total effect. So that is kind of a bad adjustment set. Now, country and project, that's the one I actually like most. For some reason there we have only one of these biasing paths, but we have this over-control thing there. So that's kind of pretty good, but still we have not identified the total effect. And then there is the adjustment set project country and survey characteristic, which gets rid of all the paths that run over selection, but we get another over control bias here. Bottom line, there is not a single adjustment set that allows us to identify the total causal effects. There are only, we have defined 4 sets which have their pros and cons. And what we later do is we use all 4, hoping that the true effect is somewhere in between. Also, there is no guarantee for this because they are all biased. And then among those, I would say sets 3 or 4 are the best. I am inclined to think that that set 3 is the best, because I believe that this those 2 paths that are there should not be so important, but that's more an emotional feeling than a real argument. And others might say that this here is the better one. Okay, so that's an open question. Also, actually, among the authors, we have not fixed that. Now, the adjustment set for time and on non-response bias. Here, since we have our measured variable in bias, the non-sampling errors come in. So there are another paths that go over non-sampling errors, which we cannot observe or which we have not observed. And that's a problem for us. So to get closer, we argue in the paper that actually in our case, where we use gender as the variable of interest y, non-sampling errors are perhaps not very important. So we kind of assume that away for the moment. Assuming this away will remove that error here, and we end up with the very same situation as before. So we use the same adjustment sets. None of these adjustment sets identify the total effect of time on bias, but we hope that the truth lies somewhere in between. And finally, the adjustment set for non-response on non-response bias. This is the situation where we just use the bivariate effect that is biased throughout. This is there is only one ingredient of this association that is what we measure, that is this direct effect of non-response to bias, but all the other stuff is really deep red and biasing everything throughout. However, if we control for country and survey characteristics, none of these biasing paths are still there. And there's also no over-control problem here. So this is an adjustment set that identifies, under the assumption of this stack, the causal effect, the total causal effect of non-response on bias. And there's another adjustment set, that is that one that additionally controls for project, which also identifies the causal effect. Set 1 is a little bit smaller than set 2, so when it comes to parsimony, you would like to use set 1, but I usually, in this case, recommend to use both sets, since this is kind of a robustness test. They both identify the same theoretical parameter, so we could use both, and they should end up in the same coefficients, more or less. And finally, there's another set, and that's the empty set, if we are still willing to assume that there is no measurement error in Y. Then all the other biasing paths also disappear. But we do not show the results of this in this presentation. We might want to add this to the to the paper. That's a new idea that I had when I did these pictures here. Okay, so the operationalization of the variable. So we use an internal criterion of representativeness, which is basically this formula here. P heads.I, where I is the survey, minus 0.5 divided by the square root of 0.725 divided by n, where P is being the proportion of women in 2-person households inhabited by heterosexual couples. In this subset of the data, the true value of P is known. It is 0.5. Among the subset of heterosexual couples, the proportion of women is 50% by definition. So what we do is we try to identify this subset of the data and look how large the observed proportion of women in this subgroup is. And then we compare both to another by the formula here in the nominator, and then we divide by the standard error of all that in the denominator, so that we can expect that the non-response bias is somewhere below 1.96, and only 5% of the non-response biases should be larger than 1.96. If there are more, then this is a clear sign that there is a non-random unit non-response bias. We only use the absolute values because we don't care at this point whether we have an overhead of women or an overhead of men. So, okay, that's our proposal. It is also discussed in the literature. There's also, I mean, of course, you could also use R indicators, but they are much more complicated to get for a large number of surveys. So we stick here with the internal criteria. Response rates, we use the harmonized response rates according to the first definition of APOR. And you see that down there, the box plots, which show the distribution of these things. I haven't talked about that here, just for a matter of time, but you see the distributions here. Then the survey characteristics. I must say that we partly control for survey characteristics by design. Namely, we only use face-to-face surveys. We only use probability sampling. We have certain standards of the projects, meaning that there are no substitutions allowed in any of the projects. There are back checks used in all of the projects. So there is a control of the design that we have not measured, which, however, also means that we have some over-control bias in some of the analysis where we don't want to control for survey characteristics. It's important to keep in mind that not always this control is a good thing. It could be a bad thing in some cases. Then we measured sample type, individual register samples, household register samples, area sampling, which includes random root perhaps as the major case. There are two different ways of random roots. One first enrolls the addresses and sends the interviewers to the addresses later, while the other one is where the interviewer does the random root and starts the interview immediately, which some people call random root light. So that is all here under the term area sampling here. And then we have others, which is multi-stage, unspecified, insufficiently documented. So that's a catch-all category of all those which cannot put under one of these headings here. And we have fieldwork lengths in days or 100 days? In days, right? It doesn't matter in the end. So here is a table of the household types, of the sample types by projects in percent. So we see here, for example, that the European Social Survey uses more frequently individual registers than all the others, all the other programs, which is a sign of the somewhat higher effort that the ESS spends in their sampling type. But let me run quickly through that. Here is the distribution of the fieldwork lengths. We also see that the European Social Survey tend to allow more time for the fieldwork work, which is also a sign that they try to have a higher quality in their sample than all the other projects. We have a measure of time, which is the midpoint of the fieldwork period. We have dummy variables for the projects, and we have dummy variables for the country, for the countries. And finally, the estimation. For the estimation strategy, we use a non-parametric regression analysis conditioned up on some covariates. So that's this lowest here, that's the locally weighted scatterplot smoother. We use mixed models using country I to allow intercepts and some slopes to vary between the countries. And then we also use a two-step approach. That means we do country separate models where we allow all parameters to vary over countries. In all these cases, the parameter beta 1 is the parameter of interest. So we look on the on beta 1 in the regression of response rate on time. We look on the parameter beta 1 in the regression of bias on time, and we also look on the parameter beta 1 in the regression of bias on response rate, controlling for time and other things. That's the estimation strategy, and I will now go into the results. So we start with time on response rate. Here you see the results of the non-parametric approach. The gray line here is the unconditioned association between time and response rate. The orange line is the lowest smoother for each project. And then the gray lines here are used to connect the data points from one country. So what we see here is that the response rate declines on average for each project, and as much as is it visible here in this big mess of gray lines, also seemingly in most countries. So that is what we all already kind of know from existing research, but here for much more data sets than before. This here is the parametric approach. So this here is the effect of time on non-response using the four adjustment sets. We see that we have on average a significant negative effect. So response rate decreases with time quite substantially, meaning 6 to 7 percentage points over a 10 years period. And if we look at the parameters in the multi-level model or in the bi-country models, we see that this is the case in almost all countries that we look at. There are some outliers here that look more positive, but we would consider this year as an outlier. So we would say clearly response rates decrease over time. Now time on bias. That's the non-parametric approach. We see again on average unconditional, and then by that is conditioned on project, the orange lines, and then we have additionally conditioned on country when we look at the connected points. And we take home from this that bias neither increase on average, nor within countries, nor within projects, nor seemingly within countries. What you don't see in this graph, we have another one where you can see it, is that the extremely biased cases may have gotten a bit more likely. So they are somewhat more frequently in the second half of the observation window than in the first half. But since they are rare, that is really a tough statement to say that they has gotten more likely. So this year is only the results without these extreme cases, but the lowest lines includes the exceptional cases. And here's the parametric approach. So there is a slight positive effect that is, with time, the bias increases, but the uncertainty of that is really very, very large in comparison to the size of the effect. So none of these coefficients are significant. If we look at the multi-level models, they are all very, very close to zero. If we look at the by-country model, where we do not borrow strengths from other countries, we see a large variation, and approximately 1/2 of the countries have a negative time effect, and the other half has a positive time effect. So we do not see really an effect of time on non-response bias. In that sense, the non-response bias seems, the probability sample seems to be fairly robust against decreases in quality. And finally, here is the result on the effect, on the total effect of the harmonized response rate on the absolute unit non-response bias. We don't see consistent effects of the response rates on bias. So we see here in the EQLS that the non-response bias kind of increases with large response rates. So that's the other direction than you would expect. We see in the ESS a slight decrease in absolute unit non-response with harmonized response rate, but the results are not that all clear. We see in the EVS almost no effect except for very, very high response rates here. And we also have almost no effect here in the ISSP. There are some suspicious cases with very high response rates and high biases in the EQLS, which are perhaps due to measurement errors. Here are the results of the parametric approach. So we see a positive effect, which is in opposite two directions. So we should expect a negative effect. The higher non-response, the lower should be, the higher the response rate, the lower should be the unit non-response bias. The higher non-response, the higher should be the unit non-response bias. So I don't get my words right. What we expect is a negative effect, but we expect a positive effect here. It is not significant. We see that in the multi-level models, the effects tend to be rather small. In the by-country models, we have again this split half thing that approximately 1/2 is negative, the other half is positive. So the effect is opposite to standard whispering, but in any case, it is not significant by standard thresholds. So there's not a clear effect here. So that's about the results. So here are our takeaway messages. Did decreased response rates deteriorate the quality of European social surveys? in the sense that we analyze here? No. Yes, the response rates decreased substantially over time, but no unit non-response bias did not increase over time, and no low response rates did not increase unit non-response bias. So these European high-quality probability surveys demonstrate astonishing robustness against potentially quality deteriorating evolutions. It could be the case that the survey institute took costly measures to counteract this evolution. That might be the case, and we believe that is the case. But then our message is that, okay, then this measure has been successful in a sense, at least according to the criterion that we used here. So we would say that popular arguments for reverting to non-probability surveys are based on false assumptions, and that is that these low response rates are a huge problem for probability samples. That might be the case, but according to our criterion here, it is not. So that's all from my side. I'm happy to take your questions, and I suggest that Marta takes the questions on the data analysis, and Piotr takes the questions on the data set, and I take the questions on the DEX.